this presentation.
No, I mean to say the letter. The letter.
Okay, yeah, of course.
That one already, the tender is out, right? You already submitted?
Yeah.
Oh, okay.
I have submitted last month.
Oh.
So this quotation now is in university level.
Okay.
Rector.
So we expect the outcome this month or next month?
I hope this month, but because of in Indonesia Idul Fitri, so I think they give me announcement next week, next month. I mean, May.
Okay.
Halo Pak Zulfikri. Wait. Maybe we are waiting for end user.
Okay.
End user is a consultant company.
Okay. So that is PT Quancons?
Yes. Quancons Forensic Indonesia.
Okay.
Assalamualaikum Pak Aco. Assalamualaikum
Pak.
Iya Pak. Alhamdulillah. Saya buka gitu Pak Aco ya, biar kita mulai Pak Aco ya. Saya Pak. Oke. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, good morning, Mr. Anup and Pak Franz. Good morning, everyone. Sorry. This time we would like to have a presentation from about the geopenetrating radar and discussion with our customer, Mr. Acho from Quant Forensic Indonesia.
Okay, Pak.
And also we will have a discussion. So this time maybe the presentation from Mr. Anup ya. Pak Acho mungkin nanti langsung aja tanya boleh Pak Acho ya. Saya sama Pak Fransi bahasa Indonesia, Pak memang dia bahasa Inggris gitu. Nanti cek aja Pak Acho. Pak Acho detail-detail tanyain aja semua biar nggak ada yang jelas gitu.
Baik Pak.
Oke, Pak Anup.
Ya.
You can start.
Okay.
Okay, Anup. Please start the presentation.
Okay. So, am I going to, continue in English? Everybody, they can follow English, or you would want to translate at the same time?
Yeah. Halo, Pak. Pak.
Yeah, please.
Okay. Anup, maybe you can explain in English without the translation. Okay.
Good morning, everybody. This is Anup Thomas here from GSSI. Thanks for coming on today for hearing something on Gpr systems. So I hope this session would be informative to you. So today I would be generally my plan is to just go through some on the company GSSI, the Gpr, the concepts, how it works, Gpr, and the systems, Gpr products which are being used specifically for geological
recording in progress.
Geological applications, how they are being used, and also we will share. Sorry. Yeah. Okay.
Please continue.
Okay. And also, I would like to share something on some data samples, so you get an idea of how what the data from a Gpr will look like, and at least you get to know what you can expect out of a Gpr. And then later we can go, we can have questions and we can discuss more. Or in the middle of the presentation also, please stop me if at all, if you need clarification or anything. Okay, so just giving an introduction on the company, GSSI, we have been there from 1970s. GSSI is a company who started manufacturing GPRs all the way back in 1970s. In 73, we started manufacturing the first GPR system. And today, we are part of a Japanese company called as OYO, which owns many other geological and geophysical instruments and products. So OYO is the parent company of GSSI. So we have other companies like Geometrics, Iris, Robertson. So these companies all manufacture geological instruments. So, but they are our sister concerns. But I would be taking care, and today we will cover only products from GSSI. Because GSSI is primarily into ground penetrating radar. So GSSI is based in the US near Boston. A small company with around 100 employees, with more giving importance to R&D and training purposes. So as you see in the picture, we have a wide range of products, except the vehicle which you see here. All are products being manufactured by GSSI. So as you see here, GSSI does not manufacture anything else other than GPRs. So we are a GPR company. We manufacture only GPR related products, only ground penetrating radars. So just coming into explaining on basically what is GPR. So GPR is the short form for ground penetrating radar. So it is basically radio detection and ranging. So you're transmitting electromagnetic waves, electromagnetic signal into the subsurface below the soil, and you get a reflection, and it is recording these reflections. So that is what happens in a ground penetrating radar. So it is electromagnetic waves is being used into the subsurface, into the soil. So there are various applications, but today we will go specifically for geological or deep applications. But it's been used for a wide range of applications like concrete inspection, utility mapping, forensics, geology. So there are a wide range of applications. So today we'll just concentrate on related to geology or geophysical applications. So how the GPR works is, so it is something like you have the GPR is going to transmit electromagnetic waves into the ground. So it is just like the image what you see here. Just let me get. Yeah, sorry. So as you see here on the left side, you see a person being shouting and getting reflections back. So same way in a GPR, a GPR system or an antenna continuously transmits electromagnetic waves into below the soil. Okay, the electromagnetic waves passes through the soil, and you get reflections back from the soil due to various changes in the soil conditions. So whenever the soil property changes, you're going to get a reflection. So if there is a bedrock layer or a water table, or soil changes to clay content, whenever there is a change in the soil, you're going to get reflections. Okay. So in the GPR, in the processing system, what we do is we record the time taken. The time taken, how much time it takes for us to receive the reflection. We also record the amplitude or the strength of the reflection, and we also take note of the phase, whether the amplitude is a positive or negative. So so the GPR basically is a product. The basic thing is it is measuring the two-way travel time of the reflection back from the soil. Also, how strong is the reflection? That is denoted by the amplitude and the phase. So if you look at this image, this is a sample image, what you see here on the right side. So this is a typical GPR image, an example of a GPR image. So your vertical scale could be time or depth, and this would be your distance on the ground surface. So this is a single scan. Okay, what you see here is a single scan, and many scans applied together, you get a GPR image like this. So this simple scan, as you see here, there are reflections. So whenever there is a reflection, you get a spike in the data for a single scan. So what GPR measures is the time it takes for each of these points. How much time it takes for each of these points. It's made up of many points, this signal. So each of these, the two-way travel time for the reflection. It also measures the amplitude. So you can see here, the signal has various amplitude. Like here it is a different amplitude, here a different one, here is a positive amplitude, that is a phase. So whether it's a positive or a negative, high positive, less negative. So it is continuously the GPR is recording all these information into the system, so that we get information on what is happening on the surface. So this is again another slide where I just want to explain how these reflections happen. So GPR, it has basically an antenna. An antenna is something which transmits the signal down. So as you see here, the antenna is transmitting into the ground subsurface, and you get reflections back. You continuously get reflections, and some of the signal keep passing down, further down. And eventually you get a signal, a scan like this, a single scan like this. So you can see the reflection happens whenever there is a change in the soil property. So if it is a single homogeneous soil or medium, you will get a single, image continuously like this. So whenever there is a change in the property, you're going to get a spike like this. The data, like the amplitude suddenly changes, as you see here. So basically it is the change in the amplitude, and you have the GPR continuously makes scans. So this is a single scan. You keep collecting many scans like this. Scan 1, scan 2, scan 3. Okay. So you get, and then we apply in the software, you apply color shades, color shading, so that like you can put like white shade to the positive side and black shade to the negative, and eventually you get a data like this. So some of the geologists and geophysicists, they like to see data like this, but it is very difficult to interpret the data. So the data on the below, this is more interpretable. So the software applies more colors in order to get a more interpretable data. So you can see here, this is a typical GPR data. So you can see the layers, the soil layer here, all these things. Whereas with this data, the raw data which you see here, it is very difficult to find out where is the layer, unless you are a trained geologist or a geophysicist. So that is basically about how it works. So in the soil, under the soil condition, or anywhere in the concrete, anywhere, you need to have a change in the soil constituent in order to have reflections. Okay. So whenever there is a change in the soil conditions, you're going to see a reflection. So if there is a limestone, suddenly you will see a reflection. Again, this reflection, the strength of the reflection will depend on how much change in the property of the soil. So it's not necessary the signal is very clear everywhere. It depends on the soil conditions. So because it's basically physics, so the soil, whenever there's a change in the soil property, or you call it as a dielectric property of the material, of the different layers of soil, the more the change, the more it will look more evident for you to interpret the data. And one of the limitations here is when the signal is traveling through this soil, you cannot guarantee the signal will travel all the way to maybe 100 meter or 200 meter. It is impossible it does like that, because the signal, as you go deeper and deeper, the signal gets attenuated or weakened, or there is always a resistance because of the contents in the soil, the conductive material of the soil, or the water content. All these affects the electromagnetic wave, and slowly the signal will get decayed. So it is not necessary the signal will be stable all throughout. So depending on the soil condition, you may not get, or you may not be able to reach very deep. So, but generally the low frequency antennas will go deeper. I will explain about low frequency antennas in a short while. So some of the applications, apart from the main applications like utility, which I'm not discussing here, concrete, some of the low frequency applications is for environmental studies, where it is used for soil contamination, detecting storage tanks, landfill, contaminant flow, all these things like hydrological mapping, water table mapping. So these are some of the examples where you need to go deeper and detect anomalies in the soil in order to see a variation in the soil and interpret the data. So apart from environmental assessment, there is a major application is for geology and geophysical applications, where again it is used for similar applications, similar to what it is used earlier we mentioned, contamination, landfills, all those things, geology and geophysical applications. So typically a Gpr data would look something like this. Okay, this is a Gpr data. So don't expect it to be showing like X-ray, showing exactly like that. So Gpr, it will show up a lot of information. It is up to the user to interpret the data correctly. So interpretation is very important. So if you are a trained a geologist or especially geophysicist could be able to interpret these type of data more easily. But for others, over a period of a time, you get used to seeing the data, you could interpret the data. So as you see here, a typical Gpr data looks like this. So this is a 2D data. 2D data means you have your vertical scale is your depth. It can be your depth or it can be your time. Remember I mentioned we are always measuring the time for the reflection. So whenever there is a reflection here, we know the time, okay? But how we convert this time to depth is in the system, we can key in how fast the signal is moving. And then depending on the soil condition, we can convert this time into depth. So this vertical scale is always either time or it will be the depth. And your horizontal scale is your distance along the ground surface. So this is your top surface. So you see this is the surface of the ground. And below the surface, you get to see many things here. So you see these curved structures, you see a long layer like this. So there are anomalies here, something here, something here. So it basically Gpr is going to show up so many information whenever there is a change in the soil condition. So it is up to the user to interpret it and identify what could be the possible cause or what is causing that particular anomaly. So Gpr does not tell you like this is a pipe or this is a stone or this is a treasure. It doesn't show you. It's up to the person interpreting the data based on background information, based on previous geological information. He may have to interpret it. But there are many tools, methods by which he can interpret it. Okay. So Gpr components, in terms of what we need to get this data, okay? In order to get this data, basically Gpr is not a very complicated system from outside, although it is complicated in terms of the data, but In terms of the system, it is a very simple system. It does not have many things like many cables, complications. No, the operation is also quite simple. So basically, a system will always, all GPR systems will consist of a topside or a control unit. So a control unit is what where you have a user interface and it applies power supply, data storage, everything is done. So we have various type of control units. That's what some of the control units, you don't have to notice about the models, but I just shared here because just wanted to explain the control unit. So there are different advantages and disadvantages of these control units. So even a tablet can be used as a control unit where to show the data. Like this is another type of a control unit where you can have more data for vehicle mount applications. So this is a portable one with a screen. So these are different type of control units. So control unit is something where the user interacts with the system, with the GPR in order to collect data. So after the control unit, the main thing is, before getting into the slide, I want to show up about antennas. Okay. So these are antenna, or you call it as a sensor. I would generally call it as antennas. So apart from the control unit, it's the antenna which is what transmits the electromagnetic wave into the soil condition, into the soil. So this antenna transmits the soil below, transmits the electromagnetic wave below the soil into the ground, and you get reflections. So it has these antennas all have a transmitter and a receiver inside. So I will go through and explain different of these models. So these all models continuously, it is left on the ground. It has to be on the ground or dragged on the ground, physically on the ground, dragged or on a wheel. And it continuously transmits and receives. So it has a transmitter and a receiver. So the antenna is always connected to the control unit using a control cable. So that's all basically. For getting a GPR data, you need an antenna and a control unit and a cable connecting these two. Okay. There are other things like you may need a wheel, all those things which are additional to that. I will explain on that. But basically, to connect something, you just basically need something like an antenna and a control unit. So about antenna, come to about antennas. So about antennas, we have different type of antennas. As you see here, the frequency, we have different frequency antennas. You can see here, this is a 2.7 gigahertz antenna. We have a 400 megahertz, 270, 200, 100, 80. So different frequencies are available. So usually, as I mentioned earlier, the signal cannot penetrate indefinitely all the way to the ground. There is a limit. So the high frequency antennas are does not travel very far or very deep. So the high frequency antennas are typically used for concrete applications, whereas you see the low frequency antennas are typically used for deeper penetration. So even if you use a low frequency antenna, still it encounters attenuation and it gets weakened by the soil condition. So low frequency antennas, the lower frequency antennas would go deeper. The high frequency antennas would be very shallow, maybe 50 centimeter or maximum 1 meter. But again, with the high frequency antenna, you get a better, good resolution. So you can detect small objects with a high frequency. Whereas with the low frequency, you would not be able to see any small objects. So the resolution differs between different antennas. So that's why we have an application guide. This is a general application guide indicating different antennas. So you can see here, you can ignore this column, just look at this column. So the primary antenna choice. So you see there is a high frequency, 2600 megahertz. It's up to 30 centimeters. So as you go deeper, as you go lower, the frequency is getting lower. You can see the applications of these low frequency are more for geological profiling, the lower frequencies. The lower frequencies can go deeper, up to 30 or more than 30, depending on soil condition again. So it primarily depends on the soil condition, whether it is highly conductive, depends on the application. Again, the mid-range frequencies like 400, even these are used for geological applications. Geological investigation doesn't mean always going for 25, 30, 40 meters. There are shallow geological applications also, like underground storage tanks and all, where you need better resolution also. So these antennas like 400, 270, 200, these are also used for geological applications. So only thing is that the depth range of them is much less. But with the very low frequency antennas, you can go deeper, but you may not be able to see small objects. Yeah.
Mr. Anup, so we can to know how deep the foundation for me. Yeah. Maybe when we use 400 megahertz, we can to know how deep the foundation.
Yeah, the foundation means because you see here, just explain to you here. Okay, if the antenna is here, okay, this is the ground surface. Okay. This is the ground surface, and your foundation, the antenna is going to transmit from the top to bottom. So you would not, you will see where is a foundation. I mean, you won't see the bottom of the foundation. Yeah, you will see a layer of the top of the foundation or something like that. You are asking whether something like a pile foundation, is it? Piling?
No, I think maybe when we use shallow foundation,
okay,
maybe we can to know about how deep that foundation.
Okay, but foundation is because it's a. You mean to say it's a concrete foundation, is it?
Yes, concrete foundation.
Okay. So basically, it's a concrete structure, correct, into the soil.
Oh, okay.
Isn't it? So basically, let me share you something.
This Gpr can to know filing between foundation.
No, the surface Gpr won't give you piling foundation. Oh. So because it's going to give you something on the surface.
Okay.
So let me just.
How much?
Just share you basically a screen here. So if you have, you can see my paint right here.
Yes, I can see.
So basically it is something like, let me just draw something. So this is your ground surface, okay, and you are mentioning there is a foundation like this, correct? Is it a foundation like this?
Yes.
Okay. So what happens is when the Gpr antenna is, suppose this is the Gpr antenna or the sensor. It is on the ground surface. You keep moving it. What you will see here is a reflection from this place, from this top surface. You cannot see what is here.
Okay.
Yeah, understood. Unless there is a way to scan from the side, which is not easy to do that. So with the Gpr, you cannot detect the length of the foundation because you are scanning from the top. But if you scan from the, I mean, if there is any, it's not possible. Like if you are on a hill, okay, if you are on a hill and suppose you scan from here, then you can find out the length. Is that clear?
Okay, clear. Thank you, Mr.
Yeah. So basically the signal is moving like this. So it is like this. The signal is like this. So basically, you get to see the top surface of this foundation. You don't see what is here.
For with this foundation, we cannot to know.
Sorry.
For with this foundation.
Yeah.
Okay. Maybe what mean Pak Acon? Pak Acon.
Yeah.
Gpr from GSSI cannot detect and measure the depth of pile foundation.
For with?
Jadi begini Pak, maksudnya Mr. Anop ini begini Pak.
Tidak dapat didetek.
Alat Gpr ini, dia ini nggak bisa mengukur kedalaman tiang pacang. Nah, jadi misalnya hanya bisa diukur itu hanya di bagian atas dari tiang pacangnya saja Pak. Nah, tetapi sampai seberapa dalam bagian bawah dari tiang pacang itu yang tidak bisa diukur.
Untuk lebar,
nah jadi
bisa juga. Apa bisa nggak bisa ya? Lebar
Oke.
atas filing gitu.
Oke. Bentar kita tanya dulu Pak ya. Anop.
Yeah.
How we can detect the width of pile foundation?
You want to detect the width, is it?
Width of pile foundation. It works or it doesn't work?
Width means, what do you mean? Width or length? Length of the pile?
No, width of the pile foundation.
Yes.
So you mean to say you want to detect something like this, is it? This is the pile. Okay, suppose this is the pile. They want to detect this one, is it?
Yes.
Yes.
Yeah, definitely you can see that in the data.
Okay.
Yeah. So the width, but the pile, normally this foundation would be to the surface, or it will be all the way to the surface, or it will be below the ground.
Iya Pak. Bagaimana Pak? Yang mau Bapak lihat itu bagian lebarnya atau bagian panjang dari tiang pacangnya?
Kalau tadi kan panjangnya kan nggak bisa itu. Mungkin kalau lebarnya ini kan
Iya,
bisa
benar.
teridentifikasi ya.
Iya, bisa. Kalau dia lebar, bisa diidentifikasi. Tetapi kalau dia tiang sampai ke panjang, tiang pacang sampai ke bawah, itu yang tidak bisa, Pak.
Oke.
Begitu, Pak. Oke.
Berapa dalam maksimal tuh, Pak?
Nah, jadi gini, Pak. Kalau untuk mendeteksi tiang pacang itu tadi itu tidak bisa, Pak, mendeteksi kedalaman tiang pacangnya sampai di berapa meter dia. Itu yang tidak bisa.
Maksud saya berapa dalam maksimal alat itu bisa mendetek kedalaman, Pak? Struktur lapisan di bawah tanah itu kedalaman maksimal berapa?
Nah, ini seperti tadi, Pak, ya, yang di bagian antena tadi itu sudah dijelaskan. Jadi ada banyak tipe antena, Pak, ya. Dia itu tergantung daripada frekuensinya dan kedalamannya. Jadi ada dia yang hanya untuk mendeteksi konkret ya sekitar 40 cm, ada dia untuk yang tanah, ada yang sampai 20 meter, 30 meter, bahkan sampai di atas dari 30 meter gitu, Pak.
Ya tadi saya lihat cuma maksimal 30 ya, Pak, ya, dengan frekuensi range zonanya tadi itu. Jadi di up 30 nggak bisa dia kayaknya ya.
Nah, kalau dia di atas 30 itu bisa, Pak. Bisa, Pak, dengan menggunakan antena MLF yang frekuensinya 16 sampai 80 MHz. Itu yang dia lebih dari 30 meter, Pak.
Ya itu jadi kalau lebih dari 30 meter maksimal berapa, Pak? Bisa 100 atau 150 meter atau berapa gitu, Pak?
Nah, itu, Pak, kalau dia yang tadi yang 300 MLF 16 sampai 80 MHz itu yang sampai 300 meter,
Pak.
Maksimal sampai 300 meter gitu, Pak.
Oke, di copy. Oke.
Ya.
Untuk produk ini kita dapat antena beragam itu atau satu antena aja ya, Pak?
Nah, jadi begini, Pak. Kalau untuk alat ini, Pak, ya, ini nanti bisa disesuaikan dengan antena mana yang mau Bapak pakai, begitu, Pak. Jadi dia sistem rakitan. Memang dia tetap kontrol unitnya itu satu. Nah, nanti Bapak mau pakai antena yang frekuensi berapa. Tetap Bapak sesuaikan dengan kedalaman penetrasi nanti akan Bapak gunakan. Kira-kira begitu.
BTW ada contoh alatnya enggak, Pak? Jadi, ini antena untuk berapa meter, ini antena berapa, bisa ditanyakan, Pak.
Oke ya. Bentar saya
gambarnya, Pak.
Minta beliau. Ya, saya minta beliau untuk menunjukkan jenis-jenis antenanya, Pak, ya. Oke, Anop.
Ya.
Anop.
Ya.
Maybe you can say the picture of type of antenna. Okay.
Yeah. I'm coming to that. Yeah. Okay. So basically, on this, what I wanted to explain is if there is a pile, the top surface of the pile, if it is below the ground surface, so you would see on the data something like this: the layer of the piling, or you would see it as a layer. So from this one, you can find out the width of the pile.
Yeah.
So you move across and you find out. So that's how you find out. So, but it is not possible with Gpr technology to find out the depth of the pile here. How deep it is not possible with them. Because you are scanning, Gpr is a equipment to scan from the surface. So you see from the surface. You cannot see unless you can see it from the side on a hill or anything. Okay.
Yeah. Okay.
Let me get back to the presentation.
Antenna.
Okay, this is about the control unit. We're talking about the antennas. So these are the different antennas. So some of the low frequency antennas which I want to introduce. So these are, as you could see here, these are all in an order like very low frequency to medium frequency. Okay, I have not put in any high frequency. We have high frequency also, but I have not put in here high. So the lowest frequency we have is around 16 megahertz. All are 16, 20, 35. This is one antenna which has multiple frequencies. Then we have 100 megahertz antenna, bistatic. So these are different combinations of antennas.
Yeah.
I show you the picture also how it looks like. So this is 100 megahertz, the 100 megahertz antenna, which can go to around, you can use it in two configurations, one up to, you call it as a monostatic. Monostatic means you have only use a single antenna. So the transmitter and receiver is into the antenna. Okay. Or you can use it as a bistatic. When using it as a bistatic, you can go more deeper because the transmitter is here and the receiver is here. It is separated out. So it can go deeper because the transmitter and the receiver is separated out. You can go more deep. So you can go to around 25. It depends on the soil condition. These depths is not mandatory. It depends definitely on the soil. So some places it may work that deep. So unless we try out, we won't know at that particular site. It depends on the soil conductivity, all these things. So the 100 megahertz is something like this. It is a shielded antenna. So you can use it as a monostatic or a bistatic. And you have a cable connected direct this to the control unit. Okay, so that's how 100 megahertz is used.
Okay.
This is a Mlf antenna, another antenna which is very low frequency, mostly for deep geological applications. But remember again, with these antennas, it is not very practical to observe small things, small anomalies, like a small pipe, like a half-meter diameter pipe and all to detect. You may not see. It is more useful for detecting layers, bigger objects, bigger anomalies. Okay, so you cannot see smaller changes with these low frequency because when you go deeper, when you go lower in the frequency, your resolution is sacrificed. You cannot get smaller things. So this is a low frequency. You can see here the low frequency is completely different. Like you have a transmitter and a receiver here. So this would be the transmitter and this is the receiver. And you see this orange elements, the long pipes on the side of this antenna. So these are the transmitting elements. So you can adjust the length of these pipe because when we supply the antenna, it comes with adjustable lengths of these pipes. So you can adjust this length of these, you call it the elements, to lower the frequency. So the more longer, you can see here, this is more longer than this one, the lowest frequency. So you can adjust the length for various frequencies from, so this would be 80 megahertz. This length is 80 megahertz. So if you go very long, it would be 16 megahertz. So you can change for different frequency by 16, 20, 40, 80, different frequencies by changing the length of these elements. And this antenna is again connected by a cable to the control unit, and on the control unit you can collect the data. And there is a cable connecting, a short trigger cable connecting between the transmitter and the receiver. So this is the link because the receiver need to know when it is transmitting. So you need to wait. So that is the link between, there is a fiber optic link which sends that trigger to the transmitter. So that's a link. So this is the Mlf antenna, which you can go for 25, 30, 40 meters. In Indonesia, we have sold these antennas for the major geological institutes and all. They have these antennas. And this is another antenna. Again, this is a 200 HS, which can go to up to 5 to 10 meters under ideal conditions. This is a digital antenna again. It's also a completely wireless antenna. There is no cable also. So you can either connect it to a tablet like this or a controller like this. So you can view the data in real time on the controller or on the tablets. So this is 200 megahertz. So this is compared to the MLF. This is much higher frequency. So this can be also used, for foundations and all, since your depth depends on if you're looking for something up to 5 or 10 meters, this would be much better than using a very low frequency. This is a 400 megahertz. Again, can be used for detecting anything up to 3-4 meters. You can use it in different configuration. You just pull it like this, or you can use a cart. So these also considered a low frequency for geological applications. It is being used. This is another 200. We also have another 200 analog antenna also. This is similar to the 200 HS, what I mentioned earlier, but this is another model of the analog antenna, like a cable. It is connected over a cable to a control unit. So apart from these antennas, you will need various accessories, something like the wheels. So the wheel is used generally to measure the distance, how far you are moving. Because when you're collecting a data, so if you're collecting a data, you need to know what is the distance, the chainage. Like this is 0, 5 meter, 10 meter, 20 meter. You need to know how far you have moved. Or if you want to find out the width of the foundation, you need to know how much you have moved. So that's why you need accessories like these wheels. So you can have different type of accessories, like you can put it on a cart. The wheel is used for measuring distance, different type of carts. We have fiber optic links for linking these two, the transmitter and the receiver. So those things. So as you see here, this 200, you have the transmitter and the receiver inside. But these ones and the MLF all have separate. The transmitter is different, receiver is different. So when you have two different elements, you can go more deeper. You can separate them out and the signal will go deeper. So that's the concept of using lower frequency antennas. So is that clear on the system? Then I can just wanted to share some data samples also. On the system-wise antennas, any doubts on what you saw?
Okay.
Yeah. So basically, these are all ground-coupled antennas. I just want to add, these all are generally dragged on the soil. Continuously, it is dragged on the soil, on the ground. So it is basically, it is all has to be in touch with the ground. So this particular antenna, normally it is usually it is going for very deep application. So normally you don't drag it. You just normally the application is most people apply it by placing it in one place and moving it to another. Take measurement, then move it to another place. Then take measurement, then move it to another place. It's something like that. So we use. Just wanted to share an image of one data. Let me see. Just a minute. Can you see this picture?
Yes, yes, sir.
Yes.
Yeah. So this is a picture of the MLF being used. This is in Indonesia, one of the geological institutes. This is this frame is made by the user. So we don't supply this frame. So the user made this frame and for carrying it. So this is the transmitter, behind is the receiver, and they move it and collect it. So this is an example. So they could use it like this, or they could use it like this also. Like individually, they can take measurement, then move it to the another place, different measurement. So there are different ways of using the antenna. Of course, it is large. It is not very user friendly, as you can see, but it definitely based on feedback, it gives good data for deeper applications. Okay, just sharing you. So wanted to share some data samples. So this is an example of data what you see from bistatic 100 megahertz antenna. Earlier we saw 100 megahertz antenna. So what you see here is you could see the layers here, things like this. So you can see this is I think this one is in meters. So it is around 8 meter, 4 meter only. They collected like this.
For this picture, how to know to identification every soil layer? Maybe we want to know this subsoil or rock or another.
Oh, that is yeah. That's what GPR would not give information. I mean, it's that is up to the person detecting. I mean, having the interpreting the data, he may have to interpret it. So generally, if these reflections, you can see here, there is a layer here, okay,
Yes.
and there is another layer here also. You can see there is another layer here also. There is another layer here. So it is up to the person. I mean, based on geological knowledge, he will have to interpret what it is. So generally, there are some rules like how you find out. Like if you see a thick layer, that means the soil, the property is drastic change in the property is happening. Then you see a very thick reflection. So if it is not a very high change in the soil property, the reflection will not be very clear. So you can see here, there is a layer here also. It is not very clear, correct? This one is also not very clear. This is very clear.
Okay.
So, so it depends on how, going back to one of the slides here. Okay, so here, when the antenna encounters layer, okay, here, the layer, if the property of this material and this material is much different, then you get a reflection. Okay, if the property of this one and this one is not much different, you may not get this higher reflection. The reflection would be very small. Understood?
Okay.
Yeah, yes. Okay. It depends on the medium. So if you have a general idea of what is in that area, you may be able to interpret what could be those layers. So that's how it works. So, but GPR does not tell you what is that, what is the color, what is the temperature, all those things. It will not give you those information. It just shows up whatever, whenever there is a change in the soil, it's going to show up like this. And the more, the better, and the more the change, it's going to show the more clearly that layer. So if you have a metal, for example, if you have a metal piece, metal pipe here, it will show very clearly. Whereas if you have a PVC pipe, it will not show very clearly because from the PVC you don't get much reflection. From the metal you get a very good reflection. So same way, it depends on in the soil so many constituents. It depends on that. So it's up to the user based on that to find out whether it's a metal or a PVC. So this is an example of a sinkhole data. So the sinkhole happening here. You can see here this is in nanoseconds. So this is in nanoseconds. So it is around 2-3 meters only. It's in the time you convert it into depth. So this is a sinkhole data. You can see there's a variation in the soil here. So basically it gives you area where there's a change. This is an example of a 200 megahertz antenna also. Something below the ground, there is a change. So we don't know, I mean, what is causing this change. That is again up to the person interpreting or studying that area to at least point out, okay, there is some anomaly in this area, we need to investigate. So then they go back and find out what is happening from background information above the soil. Maybe there is some indication. So that's how they find out more. So this gives you a preliminary indication of what is happening. So this is on a lake. So you can also use these Gpr antennas. You can put it on a freshwater lake, on a rubber boat or a wooden boat, not on a metal boat, on a rubber boat, and you can move around and on the boat, and you could see the profile of the bottom of the lake. So this is the floor of the lake. So you can use Gpr for lake profiling also. This is another example of a 200 data. Again, like around 2-3 meter penetration, which you can see here, something here. So sometimes you can see here the data may not be that clear, but you may have to be more attentive to the data in order to visualize it more better. This is an MLF antenna with a 80 megahertz. So you can see here the layers, and you can see the top. This is in the software. We have a processing software. In the processing software, you can apply elevation correction. So if you move up and down on a hill, you can correct it. So normally Gpr does not know whether you go up and down a hill. It won't know whether you're going on a plain surface or anything. It will be like this, horizontal. Okay? It will be straight, and it will be exactly like this, straight. But if you apply the correction, the elevation correction, it will become, you can then you can get the top surface, how your elevation is changed. So if you don't apply this elevation correction here, this layer would look like this. Correct? Yeah. So that is the importance of applying elevation correction. So your layer becomes straight after applying it. So this is an example of a low frequency antenna. So with the low frequency antenna, again, as you can see here, you may not be able to see the thickness of a half-meter foundation. It would be very small. It may show up just like this, maybe. So you may have to go, if you're looking for something smaller, you may have to go for a higher frequency. So the lower frequency, it is more better, I mean, for seeing larger anomalies. Okay. This is another example of layers, like a backfill. So this is a backfill here. So this is in feet. So around 15 feet, around 5-6 meters. So you can see the soil. This is they have something here, and then the soil is filled up here. It's a backfill, and there is something here, deeper here, but we don't know what it is. So if you know there is a foundation, old foundation somewhere, okay, then you know, okay, this is the thing. This is the foundation, the old foundation. But otherwise, if you are going like with a blind eye, you see so many things and it becomes confusing. So if you have some background information and you know what we are looking out in that area, then it makes the dots joined up in order to get us what we want. This is another example of Gpr data for bedrock layers. So you can also, these all data in the, this is all in color, in black and white, grayscale. You can also do it in colors. So this is in color shading. You can see how the bedrock layers is showing up for fractures, bedrock layers for fractures. So some of the other applications also, this is just wanted to add, even it can be low frequency, can be used for even leakage in the pipes. So you have here, these are two pipes, and if there is water around there, you will see a disturbance in the data. It will look like this. So that is basically I want to cover today about the data and all. So effectively, Gpr is going to show up, as I mentioned here, anything below the ground. How deep you want to go, it will depend, one, on the frequency. Second thing, also on the ground conditions. So if the ground conditions are more conductive or more water content, you may not be able to get deeper. Because in the soil, definitely, as you go below, there is going to be moisture, wet. So definitely there will be alternative. So you can overcome that, but to some extent by low frequency antennas, but still there is always limitations. So is that clear so far? Anything? So let me know if any questions.
Ya, Pak Hendrik dan Pak Aco. If any question, please ask.
Okay, I think enough. Well,
yeah. If since you're all related to geology, I just wanted to share one slide of from Indonesia also, where Gpr is being used. I'll just go through a quick one if you have the time.
Okay, okay.
So this is by one of our customers. So this is how they used Gpr for different applications. So Francisco, this is Undang. Huh?
Oh yeah, yes. This is Pak Undang from Center of Geological Survey in Bandung under Ministry of Energy and Mineral Resources.
Yeah,
has used this utility scale.
Yeah. So this is a system they're using, like a 200 megahertz antenna. So for detecting some anomalies. So this is some of the cavity. This is some of the old data. Cavity limestone foundation. They are doing how the data limestone foundations. This is for concrete. How they're using it in the concrete for the concrete scanning, high frequency. This is also on the roads. This is a lower frequency antenna for coral reefs, detecting coral reefs. iron sand, the swamp deposit. So this is basically how the data will look like for lower frequency. The rock foundations, the gravel. So it is quite, the interpretation is quite important. I mean, so this is a different antenna, a different type of surface detection on the highways. Because the highway was going down, there was deterioration. They found some subsidence. So I have a video also here. Are you able to see the video?
Yeah.
So this is a water sprout coming out from the ground. So this is the water sprout which came out from the ground. So they had this. So this is the this is somewhere near Jakarta. I recollect somewhere there. Hot water, something there. The lava used to come there. So the data they performed. So this is with the Mlf antenna collected. So you get to see the faults in the ground, the movement of the plates. So this is how they do their studies and all. So this is how the ground gets broken off. So you can see this. So this is how, I mean, it gives you information on what is happening below the ground. Yeah, this is how the soil there. The roads, degeneration of the roads, all these things. This was just a presentation last time shared by one of our customers in Indonesia. So you can see here, they collected a data all the way from here to here, and they could see anomalies, and see here, we can see changes here, variations here. So geological applications. Yeah, good one. So this is again the same similar site. The water gushing out. It's a hot water coming out. So it's a very hot water coming out from the ground surface. We detect all these data using GPRs. So this is what they evaluated based on interpreting. So there is a gas chimney and the gas is coming out like this. Yeah, just wanted to share that to you. I mean, yeah.
Okay, Ano, thank you. Thank you for your
Okay.
presentation. Oke, Pak Aco,
Ya Pak.
ada pertanyaan?
Sementara
Bisa ditanyakan?
Sangat jelas Pak. Sudah.
Oke. Anop. Okay. Your presentation is clear for us. Okay. Thank you very much for your presentation. Okay. And if any customers need the explanation of the GSSI product, okay, I can contact you. Okay.
Yeah. Okay.
Okay. Thank you. Bye.
Thank you. Bye. Thank you. Yeah. Thank you, Mr. Sul. Pak Sul.
Thank you.
Thank you.
Izin live Pak.
Ya, silakan Pak. Iya Pak, sama-sama Pak, sama-sama.
Ditunggu penawarannya Pak.
Iya Pak. Nah, ini Pak, nanti ini akan saya komunikasikan dengan Pak